All right, so today's lesson is going to use no new rules. There's no new rules, but it's going to take derivatives from a different perspective. So all the derivatives that we've done so far have been set up to say y equals something, and the something on the other side has one variable in it, typically x, and we take a derivative, right? Yeah, that's how they've all been set up. However, not all the time can we have an equation solved that says y equals. So what we've been doing so far is called explicit differentiation. We just call it differentiation, but it's explicit differentiation. It's taking the derivative of y in terms of x when the equation can be simplified with y equals on one side and x's or some other variable on the other side. So this is what we've done so far. Here's what we're going to do today. Implicit. Implicit differentiation is taking a derivative of y in terms of x when the equation cannot be solved for y equals, so that you have y equals on one side and the x is on the other side. Sometimes it's just easier to do it with implicit differentiation. It's not that it can't be solved for y. It's just that if it were, it'd be really ugly and awful, and it's very easy to do it if you don't solve it for y. So in this method, what we do is we treat both x and y as variables. And you're thinking, well, yes, x and y are both variables, but the processing of it looks a little bit different because we're doing it implicitly. All the same rules apply. We've got the product rule and the quotient rule, the chain rule and the power rule, the sums and difference. We've got all the same rules. Okay, so I'll take about one more minute if you're writing something down. If you've got notes printed out, they should fill in pretty quickly. We're going to do some examples. Okay, this equation. Okay, this is like bonus points for the day, but they're imaginary bonus points. Do you know what this is an equation of? Huh? It's not a circle, but you're close. If it were as addition, it'd be a circle. Nope. Not an ellipse, but again, you're close. It's a hyperbola. Nobody gets the bonus points for today. Man, what a bummer. All right, it's a hyperbola. If you don't know what that is, it's not a big deal. We actually usually see them first in like an algebra course or a pre-calculus course. They show back up in Calc 3 for those of you who are going to go that far in mathematics. If you're not, it's perfectly fine. We could solve this for y, right? We could. We totally could. But it's actually really easy to do implicit differentiation for this. And if we solved it for y, it would create a messier process. So this is my first example because I want to show you how beautiful implicit differentiation can be. All right, so the first part is going to look exactly the same. What's the derivative of x squared? 2x is it. Now, you haven't actually taken a derivative of y except to say y equals, it becomes y prime. But what do you suppose the derivative of y squared should be? 2y. So it is 2y with one caveat. So there's a negative here and it's 2y. When we have y squared, we actually are treating y much like we did before. When we had y equals and we had all the stuff and we took the derivative, it became y prime, right? Yes, okay, good. I want to use a different notation. You can use y prime if you want, but I think it will be easier as we work through this to call it dy dx. Dy dx is another notation for derivative. Dy, like the change in y, over dx, the change in x. So it's like a slope kind of a feel to it. So instead of writing y prime, I'm going to write dy dx. If you want to write y prime, you can. The problem with y prime is that sometimes the primes get lost, and then you think you've got a y, and then we've got problems. It's a lot harder to lose dy dx in the mix. Now, when I take the derivative of y squared, it's actually a chain rule. Why? Well, the derivative of y squared is the outside, the squaring part. So I brought the 2 down and I rewrote. But what is the derivative of y? dy dx, or y prime. So every time I take the derivative of y, I will have a dy dx. What's the derivative of 25? It's 0. Okay, so far so good? Okay, we did all the calculus that we're going to do right there, but we are going to solve it for dy dx at the end. So we're going to shift some things around. So we might move, the 2y dy dx to the right, or you might move it the other direction, the other piece to the right. And then what would I have to do to solve for dy dx? Yep, divide by 2y. You notice that the 2's, of course, cancel. And dy dx then is actually just x divided by y. Now, I'm not going to belabor the point too much, but I want to show you what this looks like if we solve it explicitly. Because if you try to do that, number one, it's going to look more complicated or be more complicated. But number two, it's not going to actually look like this at the end, and it's okay that it doesn't. If I were to solve the original equation for y, I would have, this, and I'd have a square root. Okay? But it wouldn't just have a square root, I'd have a positive or negative, wouldn't I? It would. And then I'd need to take a derivative of that, and taking the derivative of this would actually mean that I have to pull a 1/2 down. Still, it's positive or negative. But I would have to pull the 1/2 down. Oh, good grief. Oh, my word. Here we go. And then I'd have to rewrite the x squared minus 25. It would be to the power negative 1/2. And then I'd have to take the derivative of the x squared minus 25, which would be 2x. I have to use the chain rule. It's simply messier. And notice at the end, it actually doesn't look the same. It looks really ugly compared to the first one that I did, doesn't it? All the processes worked cleaner when I used this one specifically with implicit differentiation. Now, on this one, did I have a choice? Yeah, I actually have a choice. Either of those are actually correct. I could do them that way. Don't always have a choice. And in fact, most of the ones in this section, you're not going to have a choice. They're not going to be able to be solved for y. Let's take a look at the next one. This is one that we could solve for y. At least we think we might. It's awfully ugly, though, because I have a y squared and I have a y. And so solving for y here would probably involve some sort of completing the square. I'd still end up with some square roots and some positives or negatives. It would be really ugly. Okay? There are a couple of things that we could do, though. We could solve for the implicit differentiation exactly like it's written, and that's okay. But it might actually be easier to not have a quotient on the left. So how could I eliminate the fact that I have a quotient on the left to start with? What's that?
Write it to the -1.
Okay, right to the -1. I want to do something easier than that. Multiply both sides by... Okay, and what's the reciprocal? Sorry.
Y over x plus 3.
Okay, I don't want the whole reciprocal. That's not helpful because then I'm going to just flip it over and have a quotient on the other side. Y over 1. Yeah. So it's not absolutely the only way to do it, for sure. But if I multiply both sides by y, I won't have a quotient rule. I'll simply have x plus 3 on the left. I'll have 4xy and y cubed on the right. Is that okay? If you choose to do the left-hand side as a quotient rule, it's okay. There's nothing wrong with it. It's just a different perspective on that. So let's take a look at this one from this perspective first. I can't remember if I have a quotient rule one later or not. If not, we'll do it on this one too, just so you can see it. I think we'll do it on this one too. Okay. So what's the derivative of x plus 3? 1. Okay. This piece right here is a what? It's a product. I have 4x times y. So I must use the product rule. The product rule says I write the first piece down and I take the derivative of the second piece. What's the derivative of y? Dy dx. And then I add to it the derivative of 4x, which is 4. And I leave the y rewritten. All right, my next piece. What's the derivative of y cubed?
Y squared divided
3y squared, and then dy dx. Okay, everyone okay so far? Okay, so just like over here, at the end I want to solve for dy dx. But in this problem, you notice there are two dy dx's, right? So the first thing I want to do is I want to get everything that doesn't have a dy dx moved to the other side. So step one, I'm going to take the one that's on the left and I'm going to move the 4y to the left. So now this piece and this piece are the only ones that are on the right. So 4x dy dx plus 3y squared dy dx. Okay, so far? Okay, if the goal is to solve for dy dx and it's in both terms, I can factor it out. So I can write this as dy dx times 4x plus 3y squared. Is that all right? And then what will I do to solve for dy dx? You bet. I'll divide by the 4x plus 3y squared. So dy dx, from this version, the way I did it, is 1 minus 4y over 4x plus 3y squared. I want to show you the quotient rule version of this just because you will have some where you might choose to leave it in quotient form and you want to know what that looks like. So if I do this from the original setup as a quotient rule says I do the denominator times the derivative of the numerator. What's the derivative of the numerator? 1. Minus the numerator, x plus 3, times the derivative of the denominator, dy dx. Is that okay? It's over the denominator squared, y squared. Now, the benefit to that is when I had 4xy before, because I'd multiplied my y, I do have just 4x now. So there is, some give and take. Derivative of 4x, of course, is just 4. And then what's the derivative of y squared?
2y.
Yep, 2y, and then dy dx. Sorry, I'm running out of space. Okay, we still have to solve for dy dx, and they're kind of messy at the moment. So while I didn't do it before, I do need to multiply by the y squared now, because that's my new denominator on both sides. So of course the cancel here. I have y, and I'm going to distribute the dy dx through and the negative through. So I've got this negative and this dy dx that are both going through the x plus 3. So I have negative x dy dx, and I have negative 3 dy dx. On the right-hand side, I have 4y squared plus 2y cubed dy dx. Okay, so far so good? What do I need to do? I need to start moving some things. Remember, my goal is to solve for dy dx, which means I need them all on the same side. At the moment, 2 of them are here, right? But one of them has shifted over to the other side. So I need to scoot them all to the same side. Just so that they'll be positive, I'm going to move my 4y squared to the left. So I have y minus 4y squared. And I'm going to move the x and the 3 pieces to the right. So I have x dy dx plus 3 dy dx plus 2y cubed dy dx. So at this point, it actually feels process-wise like what we did before. I have dy dx in every term, so I can factor it out. I have x plus 3 plus 2y cubed And over here I have y minus 4y squared. And then I divide, and I have x plus 3 plus 2y cubed. And how interesting do you think that it is that they don't look like they match? They don't match, right? These two results at the end do not look like they match. Yeah? They're equivalent. With a little bit of algebra, we could work it out to get them to match, which means that actually grading your work for implicit differentiation is very, very difficult. Okay, so WebAssign would take both answers and it'd be fine, it'd be no big deal. But when I grade it, I've got to grade your process every single time because your process and the way you did it might not match mine and we might both be correct. Okay? So keep that in mind as you're working through these, is that there's definitely more than one way to do it, and they don't really always look the exact same at the end. Okay? All right. Ready for another one? Well, we're going to anyway. All right. So the directions ask us to do the same thing. Find the derivative. It says y prime. We're going to still solve it as dy using dy dx's just because they're easier to keep track of. What do you notice in the first piece? What kind of rule? Yeah, it's a product rule. So I rewrite the first piece, and I need the derivative of y squared. So what's the derivative of y squared? 2y dy dx. And then I need to flip it. I need the derivative of the x squared. 2x. And then I rewrite the y piece. That's y squared. I have plus 37, so what's the derivative of that piece? 0. Write it or don't. And then it equals 4x. What is the derivative of 4x? 4. This one's easier than the last one, isn't it? I only have even one dy dx to deal with, so I'll just leave that on the side where it is. So I have x squared. I'm just going to put the 2 in front, so 2x squared y dy dx. And on the other side, I will now shift the 2xy squared over. And then what? We divide by the coefficient piece that's not dy dx anyway, the 2x squared y. I bring this one up to you, not because it's any more difficult, because it's actually easier, but what do you notice at the end happens that we can still do? Anybody see any simplifying that can be done? Yeah, these are all even, right? So since they're all even, we will factor out a 2 or divide by a 2 from everything. And so we have the dy dx left. So in terms of simplification, this one had this additional step at the end that we need to take. For our final answer. Okay, ready for some trig? Sine. When it's written like this, sine xy, there are some understood parentheses. We've talked about this before right there. So what can you tell me about sine xy? What derivative rules are we going to need to use? I mean, obviously sine, but what else? Chain rule, because I've got something inside of sine. What else? Product rule, because what's inside is a product, right? So we're going to have a lot of rules for that simple little sine xy thing that's going on there as we process through it. First, chain rule, the outside. What's the derivative of sine? Cosine. Good. And we rewrite the inside exactly like it is. Okay? So that's the derivative of the outside piece. That is the sine function. Next, I need the derivative of xy, and xy is a product. So for the product, I start with rewriting x, and then I need the derivative of y, which is dy dx. Then I add, I need the derivative of x. It's 1. And I rewrite the piece that's y. The other side's much simpler. Derivative of x squared is 2x, and the derivative of negative 3 is 0, right? Okay. One of the reasons, just because, besides the fact that this has that chain rule and product rule going on that I wanted to use it for, is that I want you to see that this cosine of xy is going to distribute across the parentheses. So I've got to distribute it to this and to this before I start to try to, that's one way. I'll show you another way here in a second. Before I start to try and solve for dy. This is one option, okay? So if I do it from that perspective, what happens at this point is that I would have cosine of xy, and then I'm going to put my x at the beginning and the dy dx at the end, but you don't have to do that. You could stick them all together. Just make sure if you do this that the xy is in fact in parentheses, either whether you're putting it at the beginning or the end. Keep that xy in parentheses so that you don't accidentally see the xy and then multiply xy times x, because xy is not multiplied by x. The cosine of xy is. All right, the other piece is that I'm supposed to multiply the cosine of xy by y. So again, I'm going to put the y at the beginning and write cosine xy at the end. Okay, so now that it's in this form, I've got it much more like the last problems that I was doing. The dy dx piece is here. This piece doesn't have one, so I'm going to move it to the other side. So I'll have the first piece rewritten, x cosine xy dy dx equals 2x minus y cosine of xy. And then what would I do? I'll divide by everything that's not dy dx, which I wrote in front, x cosine of xy. So one possible answer here is, dy dx equals 2x minus y cosine of xy divided by x cosine of xy. Let me show you one other possibility. If I take this step right here and I don't distribute, okay? But instead, I notice that the cosine of xy is multiplied by stuff that has the dy in it, dy dx in it. I could simply divide by the cosine of xy at that point. That's another option. So let me copy this and do that. And we're not going to use these. So instead of distributing, we're going to divide by cosine xy. So now I have x dy dx plus y equals 2x over cosine xy. Is that all right? We could do that. Then I need to subtract the y to the other side, right? Because it does not attach to the dy dx. So I have x dy dx equals 2x over cosine of xy minus y. And then what would I need to do at this point to solve for dy dx? I would divide by x, but if I write it as division by x, it's going to look like a fraction divided by something. And so instead of actually writing it as division, I'm going to write it as multiplying by the reciprocal. So we'll multiply by the reciprocal on this, like so. So these pieces, of course, multiply to 1. You have dy dx on the left. If I distribute the 1 over x now, when I distribute to the first, the x will actually cancel with the numerator x. So this will just become 2 over cosine xy. And then the other piece, it will just go into the denominator of the y. And this is going to be minus y over x. And once again, at this point, these two answers do not look alike. I think you can look at them and see how they would be able to be looking alike pretty easily. But which one's simpler than the other one? Well, they're not. They both have sort of some benefits to them, but they're both perfectly simplified the way that they are. Any questions on those? Okay. So just like we did in the previous sections, we did a bunch of derivatives examples, several anyway, 4 rather. And then we're going to do a couple of examples where we look at things from a graphical perspective. So on this one, we're going to use the implicit differentiation to find the derivative. And then we're going to evaluate it at this ordered pair. And previously, when we evaluated an ordered pair, we didn't need y. We just needed the x value. But look back over here, the way our answers end up at the end. Aren't you glad they gave you x and y? It's nice, because I will tell you, not all books do. Some books will just give you x and you have to find the y every single time, even if you're using it here. So our book doesn't do that. They just give you the ordered pair that you will use to evaluate. All right, so let's take a look at x cosine y equals 1. So what do you see in terms of rules that we need to apply to x cosine y? Product and chain. Product because I've got x times the cosine of y. The chain kind of is a little bit hidden, actually. The reason it's a chain is because the y inside is a function itself. So we're going to have a chain in there. It's not a complicated chain, but there is one. All right, so product rule says I rewrite the first piece, and now I need the derivative of cosine of y. So what's the derivative of cosine? Negative sign. Actually, I'm just going to put the negative in front of the x, so like this. And I rewrite the inside y. Then I need the derivative of the inside. What's the derivative of y? dy dx. And then, oops, I'm sorry. And then I have addition. And now I need to do the other way. So I need the derivative of x, which is 1. And it's multiplied by, or if you wish, just cosine of what's there already, of y. And then it equals what? Yeah, derivative of 1 is 0. Okay, all right. Good. So technically, you could actually stop right here and put in the 2 and the pi over 3 and then solve for dy dx. That would be perfectly fine. We're sort of in the habit of solving for dy dx now since we've done 4 problems like that. So I'm going to continue to do that. It'll merge everything to the other side. So I'm going to move this piece because it's negative. I kind of like moving things and making them positive. That's my thing. If you don't want to move it that way, it's fine. But I'm going to move this piece over to this side. So I've got cosine of y on the left. And I have x sine y dy dx on the right. Then what would I do? Divide by what? X sine y. That's right. Okay, so I have dy dx isolated now. And the derivative itself is actually cosine of y over x sine y. We could actually rewrite cosine over sine in a different fashion if we wanted to. There's actually a more compact way to write it. It's cotangent. That's not what we're really caring about right now because we're trying to evaluate it at a point. And I think even if you haven't had, whether you've had or haven't had trig, it's easier to evaluate with cosine and sine than with cotangent. So I'm going to leave it as cosines and sines because of what I'm trying to do next. So I'm trying to plug in x is 2 and y is pi thirds. So I have dy dx equals the cosine of pi over 3. And then I have 2, right? Yep. 2 and sine of pi over 3. Okay, so this is unit circle time. You're welcome to grab your calculator if you would like and see if your calculator can sort of support you in finding those if you're not super familiar with unit circle, which I know not all of you are. But we have the sine and the cosine of pi over 3. It's the same unit circle value. So in terms of the unit circle value, pi over 3 is right here-ish. and it's an ordered pair. Does anybody remember what that ordered pair is? There's a 1/2 and a square root 3 over 2. We just have to decide which is which. So I drew it on purpose because we know it's those two pieces. Square root or pi over 3 always gives us a square root 3 over 2 and a 1/2. And it's either like this or it's like this for x and y. And we can decide, visually speaking, which one looks bigger. So does it look like the x value is bigger or the y value? The y is bigger, right? The y value is bigger. So which of those two values is bigger, 1 over 2 or square root 3 over 2? Square root 3 over 2. So this is my ordered pair. It's 1/2 square root 3 over 2. So when I talk about like thinking about the unit circle, this is what I mean by thinking about the unit circle. You can reason through the pieces without actually having to memorize all the specific details all the way around. Sine is the y value. Cosine is the x value. And if it helps you to think about them, they're in alphabetical order. X and then y, cosine and then sine. Okay? So my cosine value, my x value would be 1/2. My sine value, my y value, would be square root 3 over 2. And we want to clean it up. We want to rationalize the denominator because we have numbers that are underneath radicals here. These 2's are going to cancel. Right now I have a 1/2, and it's divided by square root 3. So that means it's the same thing as times 1 over square root of 3. So this is now 1 over 2 square root of 3. How do we rationalize that? Right, multiply top and bottom by radical 3. So on the top I have square root of 3. On the bottom I have the 2. It's already there. Square root of 3 times square root of 3 is 3. So 2 times 3 would give me 6. And of course can't simplify because one's underneath the radical and the other one's not. So this is the dy dx value, or the slope value, at the point 2 pi thirds. And your calculator can help you to figure something out perhaps, but it can't give you this answer because it can't turn things back into radicals. That is a problem that you cannot just say, oh, I'm going to use my calculator for it. You can use your calculator to see if you're right afterwards, right? You can get its approximation and you can figure out square root of 3 over 6. What's that approximation and check them. You can check it that way, but you can't get the square root of 3 out of 6 from the calculator itself. All right, a couple more questions. Equation of a tangent line. Okay, so this is sort of taking what we just did on the last problem and doing one step further. Do you know what the equation of this one is? This one is either an ellipse or a circle. Do you remember how you tell? Coefficient, yeah. So this one actually is a circle. There's an understood 1 here and here, and they match. So this one actually is the equation of a circle. All right, so it says to find the equation of a tangent line to the given point, graph the tangent line in the same viewing window. It's really difficult to graph this on the calculator because your calculator doesn't graph circles very nicely. You can manipulate it and make it happen, but it's not super friendly to do so for our calculators. So we're probably going to draw this more by hand to sort of see that it works than we are going to use the calculator to draw it. But finding this derivative is actually really nice. So on both pieces of these, I have the chain rule, right? They're not very exciting chain rules necessarily, but they are chain rules. So the derivative of x plus 2 squared, what is it? About half of you are done with your gateway. We should be gung-ho on this. First a 2. X plus 2. Nobody's talking to me. To the 1. And then a 1, yeah? Okay, that's the derivative of the first piece. How about the derivative of y minus 3 squared? Good. And you don't need the powers of 1 that I've written in. I've just written them in to sort of check out that we've thought about that. What about the derivative of 37? 0. Okay, fantastic. So we can clean this up at least a little bit if we wish. So I have, trying to think about how much I did here. I'm going to leave it like this for the moment. 2 times x plus 2 plus 2 times y minus 3 dy dx equals 0. We could solve it for dy dx. It would be okay. But we could also plug in the 4 at this point. So since I solved it for dy dx in the last one, I'm going to plug it in the 4 on this one because it doesn't ask me specifically to solve it, generally speaking. So we have 2 times 4 plus 2 times 4 minus 3 dy dx equals 0. So what do we get on the first part? This piece here, the 2 times 4 plus 2. 12. What's the coefficient on the dy dx part? It's 2. 4 minus 3 is 1, times 2 is 2. 2 dy dx. You can probably look at this and tell me what the dy dx has to be.
1/6.
Not 1/6, but -6, yeah. So if I shift the 12, if you're not seeing it right away, if I simply shift the 12 to the other side, and then I divide by my 2, there's that -6 coming out. So my dy dx is -6. Remember, dy dx is a slope. The point is 4, 4. Yeah? So we have a slope of -6. We have the xy value of 4, 4. So y minus 4 equals m, which is -6, times x minus 4. And we can add our 4. So y is equal to -6x plus 28. Okay, we've looked at graphs from this perspective before, so for the sake of time, and I really want to make sure I get to the next one, what we would do right now I won't do, but you would graph the circle. You know how to graph a circle. At least somewhere along the way you learned the -2 and the +3 would be the center. You plot the center. Square root of 37 would be the radius, so that's almost 6. You'd go out almost 6, up, down, left, and right, draw the circle around it, and then this line would lay on top of it and would touch the line, or the curve, the circle, just barely at the line, at the at the point 4, 4. So you'll end up with a circle that will look much like, I think it's this was what it ends up looking like when we actually do it, something like that. Maybe it's up here, I can't remember where it actually touches it, because I don't remember how it all works out, but we could do that, right? Okay, let's take a look at our next one. Any idea what d2y dx2 might be asking you to do? It's a derivative of a derivative. So this is called a second derivative. And while I read it the way it really showed up, d2y dx2, what it actually says is I want the second derivative of y with respect to x twice. That's what it says if I turn it into English and I don't just read the symbols. The second derivative of y with respect to x twice. But what I literally do is just like what you said. I take the derivative once, and I solve for dy dx, and then I do it again. Okay? So let's take a look. This is a very simple example because the process gets bogged down a little bit. You'll see. What's the derivative of x squared? What's the derivative of 2y? -2y, sorry. -2y dy dx. And the derivative of 36? 0. I need to solve for dy dx before I move on. So I will move my dy dx, and it's 2y to the other side. I'll divide by the 2y. And I will find that dy dx equals x over y. We saw that earlier, actually, was our very first example. Okay, is that all right so far? It'd be great if that were all that we're asked to do, but we're asked to find the second derivative. So to find the second derivative, I need to find d, I'll change colors so that you can see the pieces showing up differently, d2y dx2. That's the second derivative. So I need the derivative of x over y, which is a quotient, right? Quotient rule says I do the denominator times the derivative of the numerator. Well, that's easy, that's 1. Minus the numerator times the derivative of the denominator. What's the derivative of my denominator? dy dx. Over the denominator squared, which is y squared. There doesn't look like you can do anything to sort of eliminate pieces in here. I mean, I can obviously write it as y and not y times 1. But there is something you can do. You know what dy dx is. What is it? It's x over y. So at the end, I can't have a dy dx in the middle of the d2x dy2 problem. I can't. All right? I have to plug it back in. So this piece gets plugged in here. So now I have y, like I said, and then minus x times x over y squared. And I do need to simplify this. So one of the things that you might do is that you might say, okay, well, I'm not going to write division specifically by y. I will rewrite this, all of it, to be, well, this is x squared over y, to be times 1 over y squared. Right? Write it as multiplication by the reciprocal. And I can distribute it through. So this would give me y times 1 over y squared. What would that be? It would be 1 over y. And then on the next piece, it'll give me x squared over y cubed. Could they be combined into a single fraction? They could. Do I need to? No. It's fine the way that it is. All right, any questions on that? Oh, you know what? I know what it is. There's one other cool thing that can happen. I'm going to bring it up, not because you have to notice it and do it, but there is actually, if you tried to combine them, you'd have actually y squared is enough. There is an interesting thing, and if you see it, you're going to be like, I don't know what they did. Now you will. Okay, so this is what it is if you combine them, right? What is y squared minus x squared? It's negative 36. Where did negative 36 come from? Yeah, the original problem, this one has an interesting way. They don't all simplify like this. This is not a normal thing. But this one does, if you get to this point, have the ability to change like that. So if you see something simplifying or you're like, I think I've got the right answer, you might do a little bit of manipulation to see if there's a simplification you didn't recognize at first. Okay, not something to be super worried about, but just to be aware of it being a possibility.